pues no sé si ya conocéis a Sebastián González, ¿vale? Que hace su tesis con Víctor Vilaraza y yo creo que también Marco Dens, pero no sé si está muy metido. Y bueno, pues trabajo en estas cosas hidrogeoquímico, mecánico y tal. Y bueno, entonces hace su proyecto, bueno, su tesis doctoral sobre ello. Y bueno, nos va a contar lo que está haciendo, ¿vale? Pues, I don't know, we do it in English or?
It's in English, I guess,
Yeah.
because it was in English.
Okay, we speak in English. Sorry for having spoken in Spanish, French speakers. For the Catalan speakers, sorry, French. Okay, so the floor is yours.
All right, thank you, Martin, for the introduction. Good afternoon, and thank you all for coming. For those who don't know me, my name is Sebastián González Fuentes. I'm a geologist, and I'm a PhD student, well, from here, from the UPC, but I'm conducting my doctoral research just across the street in the IDAEA-CSIC Institute. Today, I'm going to be talking about the first part of my doctoral research project, which is titled Coupled Hydrochemical Simulations of an Engineered Concrete Barrier in a Geological Repository for Nuclear Waste. This work is part of the mechanical etching of cementitious materials MAGIC project from the European Joint Program in Radioactive Waste Management, which has received funding from the European Union's Horizon 2020 Research and Innovation Program. Before moving on, I would like to mention, as you said, Martin, the supervisors of this work, which are Víctor Vilaraza from the IDAEA in Mallorca. Well, there's also Martin from here from the UPC, and there are some other collaborators like Pep and Jordi that are all here actually, looking among others from the Spanish National Research Council. So let's get started. The interest in the study of a concrete engineered barrier is to assess the utility of the structure that supports a high-level nuclear waste disposal cell in the long term. For those who are not familiar with this type of waste, they are characterized by having high activity, being strong heat emitters, and they are mainly constituted by spent fuel rods. The picture in the left shows a rod being dropped into a cooling pool, in which will be there for many years until it's safe to transport it to its final disposal site. The figure in the right is a conceptual scheme of a deep geological disposal facility, in which the area of interest in this study is the support structure of a tunnel within this underground facility, just like the one which is shown in the zoom in the figure. For being more in particular, it is this cylindrical structure which is in contact with the host rock in this facility. What we have researched and found in the literature is that in recent years there's a need for accurate and more powerful computational methods for material science, in material science. For example, reactive transport, which is mainly used in the context of containment transport processes, now has grown to tackle also materials degradations, like a phenomenon that can take place in radioactive waste repositories, where the impact of geochemical reactions can significantly alter the properties of the medium. We also found in the literature that the geochemical response of materials chemically affected has been usually neglected for calculations. This is due to the fact that considering coupled descriptions of a model can significantly increase the complexity of the model formulation. Last but not least, it is important to note that it is in order to approach the hydrochemical behavior of cementitious materials, not only because the experimental data is limited to the short term, This is because the experiment that has been carried out just started at most a few decades ago, but also because the long-term data at the time can be only reached by numerical simulations. When we speak about long-term in these particular problems, we're talking about periods of times within thousands to millions of years. Well, instead of all this, the methodology that we propose to achieve our purpose is the development of different predictive models. The initial idea is to develop a hydromechanical model. Secondly, to develop a hydrochemical reactive transport model. With the aim to couple these two models into a hydromechanical model to finally run simulations of the problem that we are trying to approach in the long term. Well, as just said, we started with the assessment of the hydromechanical model, in which we created a 2D plane strain model using code, which is developed here in the UPC, and I'm sure that most of you have heard about. Then we selected a linear elasticity constitutive model for the program in a saturated medium, and we then developed a 4-stage model sequence to simulate the tunnel construction. Each of these stages were, the first one was the equilibration stage, in which the model took 200 days to reach the steady state of the problem. Then there's a second stage, which is the excavation stage, in which there's a cut in the domain of the model, which is a circular cut in the center of the model domain. And we set for the excavation stage a period of time of 7 days. After the third stage of this sequence is the lining or support structure construction, in which we create this concrete lining around the circular cut surface that we made previously in the previous stage. And we selected a 1-day period of time of the time that's spent in the construction of this support structure. And then there's the fourth and final stage, which is the evaluation period in which we selected a time of 25 years. This is standard that we selected because we saw in the models that at this time we were able to observe an equilibrium of the variables, but also it is a reasonable time to test and modify the models, so we can check different modification in the variables. Well, so far this is the model which we're going to name a base model, because in the hydromechanical part of the project we not also made one model, but we also make another one, which we're going to name the alternate model, in which we were trying to simulate before moving to the hydrochemical stage of the study. We were trying to simulate a damaged support structure in the interface between the support structure and the host rock. Well, just like I said before, going to the hydrochemical simulation. This is for comparison purposes, and actually, and also it's like a rough way to try to compare these two models, because in this model we are going to simulate a damaged support structure just by decreasing the young modulus and increasing the porosity in the material in the concrete rock interface. But we're running these simulations since the beginning. I mean, we're going to have these properties since the beginning of the simulation in the program. So this is not a realistic case, because we expect that this damage into the support structure happens over the time, not since the beginning of the simulation. But at least it's like the worst case scenario of simulation if we select these characteristic parameters since the beginning. So the results that we found comparing these two, the base and alternate models, the first one that we found was we expected, and also we observed displacement in the vertical and in the horizontal directions in the problem. Last time I presented this part wasn't so clear, so now I try to draw these arrows, like the biggest one in the horizontal direction and the smaller one in the, the biggest one in the vertical direction, in the smaller one in the horizontal direction. So we're able to see that the displacement were significant in the vertical direction and not much in the horizontal direction. And we also observed that in both the based and the altered model, the displacement were the same. But I think the most important observation of these results is that in both the based and the altered models, we were not able to observe positive change in the support structure in either of both models, which make us believe that the positive change that we are going to observe are going to be mainly, strictly related with the hydrochemical model, which we are about to show. And we also did some calculations with the collected data in the support structure. We selected two different control points in the top and the side of the structure. And with the collected data, we calculated the stress trajectory or stress path of this control point in both the base in blue color and the altered model in orange color. And the idea was trying to compare the stress trajectory in these control points in both models. What we were able to observe in this chart is like from the right, which is the support construction, and more to the left, approaching the failure limit, which is until the 25 year solution time period. We were kind of able to observe that the altered model could have been more affected than the base model, which led us to believe that the altered zone may affect the concrete integrity over time. Well, after the development of the hydromechanical model, what we did was the development of the hydrochemical model, which is a 1D electric transform model using Kebroff, again developed from here from the UPC, and maybe you have heard about this code. The selected input data was taken from the cement clay interaction experiment from the Monterrey Underground Laboratory. And well, there's a conceptual scheme of the hydrochemical model in the figure. As you can see, there is a 30 centimeters 1D domain within the supported structure. There are some mineral phases in this domain, which are portlandite, calcium silicate hydrate, and quartz. We model the host rock in this model as a fixed boundary condition with the pore water concentration of the material. And I think it's important to mention that at the beginning we were very optimistic in the hydrochemical model, and we tried to, for example, at the beginning, to put in contact two different materials with a complex chemical system. And we, over time, found some difficulties to make the system converge. So we were, over time, simplifying the problem until this problem, which I'm showing here. But it is important also to mention that our main goal is to observe the coupled hydrochromomechanical behavior. So we found it suitable to simplify the chemical system, so we can be able to return on those. And we also found in the literature and discussed previously that in the long term, the main transport process would be diffusion. So we only consider as a transport process here in this model diffusion. Well, for those who don't know how kickoff works, or maybe for doing a bit of marketing of the code, kickoff works like we need to create different solutions in Frixie, considering the elements involved in each material and also the concentrations. And we also need to take to make kickoff work to select a suitable database in which we can find like the mineral phases that we're looking for, and also the reactions which are going to be involved in the system. Once we run the solutions in Fixie with this database, then there's a executable in kproc which could read and write the different input files that were going to be needed in the future to run the kproc simulation, which are the local kame file and the com6 file. And to run kproc, we also need another file in which we're going to, for example, set the discretization of the domain or also the evaluation periods of time. So once we have these three different files, we can run the kproc executable to get to have this a text file with the results that we are looking for. These are some screenshots of how these files look. For example, you can see in the local kame file, there are many different phases with different species in each of these phases. And for example, there are many other variables in each of these files, but they're just showing something. And well, in the chemical system file, there are also the reactions and the components involved in the system. These are some other characteristics that we set for this model. The table in the left shows the initial solution compositions for concrete and rock, which were taken from many different authors, but all related with the Monterey Underground Laboratory. The table in the right shows the minerals contained in the domain of the problem and the volume fraction of each of them. And well, the diffusion coefficient was taken from an article from Pierre Soler, and the domain discretization was in millimeters in this model. The results that we observed are shown in these charts. In the x-axis, you will find the distance from the interface, which is from right to the left in each chart. And in the y-axis, we will find the volume fraction of the different mineral phases involved in the system. As you can see, after the first year of simulation, we are able to observe a decrease in the portlandite volume fraction value, which means there's dissolution of portlandite near to the concrete rock interface. We can also observe that related to the CSH, the volume fraction value remains constant, which means there's no dissolution yet in the simulation. But after, for example, 5 years, we observe like the dissolution moves through the material from the concrete rock interface into the material, and we are able to observe also some CSH dissolution. Then over the time, there's more dissolution of portlandite and CSH through the material, and we can also observe that the dissolution ratio is different for these different mineral phases. Here again, we can also mention that at the beginning we were considering many different mineral phases, so these were way more complex charts, but now we're just considering 2 different mineral phases, so they're this kind of a simplified model in comparison with the one we were trying before. Well, the left chart shows the evolution of pH over the time, but I would say that the most important chart is the one in the right, which shows the evolution of the porosity in the material in contact with the host rock from the concrete rock interface through the material in the left. We can see that over the time there's an increase in the porosity in the material at the beginning related with the portlandite dissolution, but then not only related with portlandite but also with the CSH dissolution. We try to see this in the final stage of the simulation. We can observe that near to the concrete rock interface there's dissolution of portlandite and CSH, which is related with an increase on the porosity into the material. Then when there's no more dissolution of the CSH mineral phase, then we can observe that the increase in the porosity in the material is only related with the dissolution of portlandite. And after that, and after affecting almost 3 centimeters into the material, we can see that we reach the original value of 15 in the material because there's no more dissolution of any of those mineral phases. And what we are trying to achieve in this last part of the study is to couple the hydromechanical and the hydrochemical models that we have already developed. The way what we're trying to do so is with the code code. And here the idea is to relate the changes in the young models of material with the changes on porosity caused by the chemical interactions between these two different materials. Some other final, let's say final, but still challenging tasks are before moving to perform the hydrochemical couple simulations, we decided to reproduce the hydrochemical model developed in Kiprov in Colorado before moving to the coupling model, and I put like a self-check symbol because we were able to do so in Kiprov and have some similar results between Kiprov and Colorado running a hydrochemical model, but we are having some convergence issues which doesn't allow us to perform the model for more than 2 years. As we can see in the simulations in Colorado, we observe Ponente dissolution and CSIC dissolution from the concrete rock interface through the material. But due to these convergence issues that I just mentioned, then we were not able yet to run simulations for more than 2 years. This same dissolution, the dissolution of these phases conduct the same increase in porosity in the material as we observed in the Kiprov model. And let's say at least we are finding the same behavior, but not with the same dissolution ratios. And then the next step would be the activation of the mechanical component. So we run the hydromechanical simulation. I tried this before in the model, and I was able to observe that the model is running, but we haven't solved yet the convergence issues in the hydrochemical problem. So there's no reason yet to move forward to the hydromechanical model, I guess. But at least I know that it is working. And the final stage of this would be to run the entire hydromechanical model, in which we are thinking about not running the whole system, the whole geometry, maybe a quarter of it, due to the symmetry, but due also because we are expecting a higher computational cost. And after this, the final idea is to run this model in the long term, which is what we're trying to approach. That's pretty much it. And these are the references. And thank you for your attention.
Okay, some comments or questions?
We have one regarding slide number 9. Values that you chose for permeability. With the concrete is 10, released rocks 10 minus 20, minus 19 concrete, and outer zone also minus 19. So they are not rather small values. Or have you played with another values, let's say 10 to minus 17 or 10 to minus 16 or something like that?
No.
So it's not, they are extremely low.
We haven't tried higher values of primarity. We just tried the variations in the younger models and the porosity. But that would be interesting.
Well, the rock is very low.
Huh?
The rock is very low.
Well, the three of them,
Yeah.
it's also for the concrete, and also an outer zone, that's the same value, same as concrete. They should play with smaller, larger utilization.
I think that we actually, I forgot, but I remember that we mentioned at that time, it was like we were going to consider only as a transport process diffusion, so the difference in the permeability wouldn't affect our final results in the coupling simulation. So I think that was why before at that time we didn't change the permeability values.
The rock, what type of rock is it?
I would say sopalinous clay properties from the in Monterey.
This is all very low permeability. There's no advection, so this now is surrounded by formation, but there is no flow. The value, the permeability value is probably something that the model requires or something that it's not really used. It's all
Because it's a closed system, so there's no water coming in or out. It's hardly any flow.
But so you mean that in the system, apart from the small value of permeability, there is no flow because of you are not imposing any gradient? There is a difference in pressure, like between the center and the outside, or it's everything at the same pressure?
While we model this,
Yeah.
we consider like a very little amount of different. I was like,
So there will be some very tiny advective flow.
Because what are the boundary conditions here for water?
I thought that we were very good about this. So there is a liquid pressure over the entire system of 5 megapascals, and then
The initial or the?
these are initial. Yeah. And then since I remember, when we excavate here, then we put like a value of 4.9, something like that.
I think you would have initially some advection, some flow, if you consider, if you have bentonite in the center, then the resaturation of the benton goes away and you have. Then resaturation takes a long time, so it takes some. Because of the suction that the benton goes, then you will have a very slow influx. So I guess in this model, this is not taken into account, but that would be very slow. I think assuming just diffusion. In terms of the alteration that we calculated. Yeah, because the rock is very impermeable, so even with the gradient, it's very difficult to make water flow. But the bentonite in the center we can impose until saturation, which happens very low. So you need to come out.
Okay.
I have a question about these conversions problems. So what I understood is that the right runs well for the geotechnical calculation for about 2 years or so, and it runs well. And then what happened?
I would say the problem explodes. I mean, no, it explodes by this area. There's like, actually we are able yet to.
I don't know, because we are sort of looking into that. But this is the direct substitution approach from Newton-Raphson, and its convergence is difficult. Okay, so there may be some error. Another thing is that we have this step, almost, the step functions. I mean, if you look at the foreground height and form fraction, the results, it's one thing, and then it changes. This is very difficult with the method, with the finite element methods, etc. Because nothing happens, or you change it very quickly to orders of magnitude. The H's change a lot. But this is difficult, so I don't know whether to, and I think this is also not, maybe not very realistic, so maybe, I don't know if it, because he assumed equilibrium, no? A bit of the chemical reaction.
Yep.
So usually if you assume, for instance, kinetic, these fronts may be a little bit smoother. So maybe
Maybe we could, at the end, the overall kinetics will be given by transport, which is very slow. So instead of forcing chemical equilibrium, you have some fast rate, but not extraordinarily fast. Maybe that's the issue.
maybe.
Because the overall evolution will be this is a transport control system, we given by the small diffusion control plant.
Yeah.
I guess you can use kinetics around
Yeah.
it, believe me.
But I guess these flows will not be that abrupt.
So, it's not so, the front is not,
No, but
the vertical wall.
yeah, but you don't have a sudden change of things from one time step to the other. And that may give a problem.
I don't understand.
For instance, if you have some mineral concentration,
Yeah.
if the CSH drops to zero,
Yeah.
then also the whole chemistry changes.
Well, I mean, you will not have, you still have diffusion.
Yeah, that's
That
what-
is silica from, you have also composition of the boundary water and the silica coming from the intact part of the rain.
I guess you also won't have a change, but when just after you reach this zero CSH or whatever other mineral phase, you have a change of chemistry, chemical composition.
Well, yeah, I mean,
Quite a sudden change.
yeah, but so maybe using kinetics is better for that,
Yeah.
maybe instead of strictly, so just a fast kinetic rate, we try different values and maybe that's.
Maybe that you can try.
Yeah, but for instance, with the modeling I've done in the past, we use Scrunch, that just uses kinetics.
Yeah.
And for local equilibrium, I mean, there's no, you cannot impose equilibrium per se, you just use the fast rate that is fast relative to transport, then it works quite nicely, so maybe that's the problem.
Could be a solution.
Maybe using kinetics is a bit, it can, from the numerical point of view.
Another thing, actually, your what happens, your phenomenon is not that complicated because you have just a zone of where the porosity
Yeah.
goes up and
Yeah.
there's a certain velocity or something, and this is diffusion control. So maybe you can do something more simple.
I mean, I would make it as simple as it can work,
Change or
but,
something.
No, I think chemically it's simple, but I think it's okay. I think those are the main phases, the main reactive phases in the.
But
Yeah.
the change is even simpler. You could predict it with
I mean, no, yeah, I can say, well, I dissolve the CSH of the problem, and then I know what the porosity is going to be. I think the point here is to couple. I mean,
Yeah.
even with a simple system, to make the coupling between the chemical part. So I think it's important that it works, and then use maybe more realistic cement composition. But I think this is simple, but it's okay.
Yeah. No,
But,
but if you, because for Colorado, the only thing that is important is the velocity.
Right, but sure, but I mean, you want to be able to solve for that porosity. I mean, yeah, I could tell you, oh, the porosity is going to be that much, but then you're not coupling anymore. Right?
Yeah, of course, you're not coupling.
I think the important point here was to look really at this coupling. I think that was an important part. Otherwise, we know how to calculate the chemical system with any number of poles. I think the important point was here to make the coupling. Well, you have a chemical calculation and even with a more complicated system, it should also work. So I know the porosity that comes out from here, so the same code and do the chemical output, the mechanical output. I think that was the kind of important novel point of the approach.
That's good.
Otherwise, we know how to do the chemical system. If you don't care about chemistry, tell me, oh, after some time, this is going to be the porosity distribution. Then there's no problem.
I'm glad this discussion came out.
Yeah, because numerical stuff, I don't know what.
But you can try kinetics. I mean, you can do kinetics with Kepler. So
Yeah, of course.
then just a simple, very simple kinetic rate, just a rate constant times 1 minus omega, something like that.
Yeah.
Taking notes.
And that's it.
Yeah, we could try that. Okay, some other questions or remarks? No? Well, then, I can do it with someone online. People online who wants to say something? No? If not, then,
No, thank you very much.
then we thank you for the presentation.
Tenemos trabajo que hacer.
¿Ya se ha terminado a ella?
Sí, yo creo que esto va bien. No sé si puede ser más
Sí, y ya de alguna de las formas que hemos intentado, como que